Welcome to the class again. We were discussing Stevenson rearrangement. I'll give you two more practice problems. When this quaternary ammonium salt is treated with sodium hydroxide, it is undergoing Stevenson rearrangement. That is 1,2 rearrangement. This alkyl group, it is undergoing rearrangement to this. That means negative charge will be generated here, then this entire group will be leaving. This is the product. So this is Stevenson product. Not only that, we also have rearrangement. That means if we generate negative charge here, that will undergo nucleophilic substitution here. So that is also possible. This product is from the negative charge generated at benzylic position. So that will undergo 1,2 rearrangement to give this. If negative charge generates here, that will undergo nucleophilic substitution on this carbon. So this bond will be breaking. Here the product is this is the product. Okay, but it is the minor one. This is the major one. Stevenson rearrangement is the major one. The final example for Stevenson rearrangements. This is treated with sodamide in ammonia. It is giving two products again here. This is the major. This is minor. Actually, the minor product is the Stevenson rearrangement. Okay, minor product is the Stevenson rearrangement. When sodamide picks up a proton here, negative charge generated here will be polarized towards nitrogen, then benzylic group will be leaving. So benzylic rearranges to this position. It is the minor product. Not only that, we can also generate anion here. When sodamide picks up a proton here, this group will migrate here. So that is the product. That is why we have ring expansion. This is 8-membered ring, but here it is a 9-membered ring. So when we generate anion here, this alkyl group will undergo migration. So we will have ring expansion. This is the product from the migration of benzylic system. So if anion generates here, this is the product. If anion is generated here, then this is the product. This is the pH. I did miss this pH group. Please take that. This is the pH group. And there is a mistake also. Actually, this is the benzylic carbon which is migrating, not this ring. Okay, this I'll write this. When a negative charge is generated here, this will polarize towards nitrogen. Then this benzylic anion will be generating. This benzylic anion will attack here. So this is the product. Now we will discuss Somlet-Hauser rearrangement. What is Somlet-Hauser rearrangement? Rearrangement of quaternary benzylic quaternary ammonium salts, benzylic quaternary ammonium salts under basic conditions to ortho-substituted amines, ortho-substituted amines via a 2,3 sigmatropic rearrangement. Rearrangement is called as Somlet-Hauser rearrangement. Rearrangement of benzylic quaternary ammonium salts under basic conditions to ortho-substituted amines via a 2,3 sigmatropic rearrangement is called as Somlet-Hauser rearrangement. When this quaternary ammonium salt is treated with a strong base, then we can generate an anion here minus. So this halide will undergo 2,3 sigmatropic rearrangement. What is 2,3? This is 1,2 system. So 2. This is 1,2 system. 1, 2, 3. This is 3. So 2,3. It is a 2,3 sigmatropic rearrangement. Now this negative charge will polarize toward this. I should have properly placed this double bond here. Okay. Then this double bond, imagine. Otherwise, I'll write it again. Now this negative charge will be polarized to have ortho substitution. Then this double bond will be polarized like this, so that the quaternary ammonium salt will take the bond pair of electrons, so it becomes neutral. Now this double bond will undergo a rearrangement, again tautomerization. This is the new double bond, so it will undergo tautomerization to generate this product. So this is what is called Somlet-Hauser rearrangement. Please take the notes. I'll give 2 more practice problems for this. What is the product here? This is generating two products. So I'll give the products. You practice how these two products were forming. This is in 58%. This is 7% only. This is the major product. We practice how these two products are generated here. Now we will discuss Neber rearrangement. What is Neber rearrangement? Conversion of O-tosylated hydroxylamines to alpha amino ketones are called Neber rearrangement. Now, how do we generate this functional group? If a ketone is there, ketone can be treated with hydroxylamine to generate oximes. Now this OH group in oxime can be protected as O-tosyl when we treat that with tosyl paratoluene sulfonyl chloride. Now this O-tosylated hydroxylamines, when they are treated with base followed by hydrolysis, they generate alpha amino ketones. This C double bond N will become ketone, and alpha position nitrogen will be migrating to alpha position. I'll give you how this reaction works. When we treat this with a base, of course, imines are almost identical to carbonyls in their reactivity. That means hydrogen on alpha carbon are acidic. So we can easily remove a proton from the alpha carbon to imine. C double bond is called imine, right? Right. Now, because we have a good leaving group, O-tosyl, this negative charge can attack on nitrogen so that OTS will be leaving. O-tosyl group will be leaving. I should have minus charge here. So what we are generating? We are generating a 3-membered ring. This is stable, this is the intermediate. This can be isolated, it's not a problem. If you want to have this product, we can stop the reaction here itself and we can isolate it. But if you want to convert this, just add some dilute acid. Imine, of course, can be hydrolyzed easily to carbonyl compound. So this is the double bond, C double bond N will be hydrolyzed to C double bond O. Because we have this bond, amine group will be there. So this is what is called Neber rearrangement. Please take the notes. I'll give 2 more examples for this. And it is treated with sodium methoxide followed by hydrolysis. The generated product is we don't need to worry much about this. The double bond N will be hydrolyzed to double bond O, and on the alpha carbon we will have amine group. Okay, so double bond N can be hydrolyzed to double bond O. Alpha carbon we will have amine. So this is what the final product is. Take these practice problems also. And cyclohexanone is treated with hydroxylamine, it can be converted to cyclohexanone oxime. Now this oxime is treated with paratoluene sulfonyl chloride under basic conditions. Base will pick up this acidic hydrogen. O minus will undergo nucleophilic substitution. Cl is a good leaving group, so it becomes O tosyl. Then it is treated with a base and finally it is hydrolyzed to get the product. Now, how do we write the product in Neber rearrangement? You don't need to worry much about this. You make the C double bond N as the C double bond O, make an imine substituent on alpha carbon. That's it, right? We don't need to worry much about it. Just convert this C double bond N to C double bond O, attach one imine group on the alpha carbon. A small variation in Neber rearrangement is N-halo groups. Because chlorines are good leaving groups, N-halo can also be treated with sodium methoxide followed by hydrolysis to get the alpha amino ketone. Here, what will happen? We have two good leaving groups, so we can generate a negative charge here as well as here. So that generates an intermediate of this kind that upon hydrolysis will give the final product. Okay, so when we have good leaving groups on nitrogen, we can perform this Neber rearrangement.